Hello, hello, hello. We are designing a computer-controlled composite pressure vessel filament winding machine. And in this episode, we'll continue from where we stopped in the last video. The last video was an introduction of the entire scope of the project. But in this video, we are doing the proper design. But right now, we're talking about the kinematics. So, kinematic design. If you have not seen the first video, it's instructive to go back and take a look at it, study, and take notes, because everything we're doing there applies here, or everything we did there. In order to discuss the kinematics, I have to draw the frame, all right? So that's what I'm doing now. I have to draw the entire machine, and the machine basically consists of a frame standing on the floor. Let's take it to 14. And then other components are attached to that frame. Back to 14. Let these represent the legs of the machine to support the frame, preventing it from falling, right? And this is the lower member. So simplified layout so that we can analyze it with ease. This is a center line representing the rotation axis of the mandrel. Of course, I discussed what the mandrel is. Basically, the mandrel is a preform that is introduced into the pressure vessel production process. It already comes in the shape and size of the final pressure vessel, but it's not by itself strong enough to withstand the pressure. This is a preform that you insert into, because with the filament winding process, you have to insert a preform there, or a mandrel. So that preform is shaped exactly like the pressure vessel we're working on, which is the 1354 pressure vessel. 1354 is a way to define the size. So 13 represents the diameter of the pressure vessel. 54 inches represents the height. So all of this is in inches. 13 inches diameter, 54 inches height. So as I continue with the drawing, now I'm drawing the mandrel, the sides of the mandrel, so that everything I'm saying will be based on something you can all see and relate with, and come and follow along with the logic and the decisions that are being made for this machine. Basically, design is a series of decision-making steps. You remember the mandrel is a cylinder, 54 inches long, but it has caps or domes on both ends, the bottom and the top, which I hope you can see. I hope the sketch is clear enough to see. So the machine consists of a frame with a mandrel mounted on it. The mandrel has freedom to rotate along its central axis, and there are components that govern that rotation. So the class of components that hold the mandrel and rotate it, we are calling them mandrel axis rotation components. Okay, so these are, let's start in a more systematic way. So our machine consists of a frame Number one, frame. Number two, a class of components that we're calling the mandrel axis rotation components. And as the name implies, they help hold and rotate the mandrel according to the computer program that we have written. So that's the first axis. The next axis we need to consider is the carriage, which is extremely important. The carriage runs all the way, all along the length of the machine. It's longer than the machine actually because um, it needs to be able to move the payout eye device. And by the way, the payout eye device is like the end effector of a robot. This is, by the way, a filament winding machine, computer controlled, is actually a robot. So in this case, we're working with three axes, although we said that we might make a decision to add a fourth axis. So this is essentially a three or four axis robot. Okay, so this is robotics, in case you were wondering. So the carriage for the payout eye device, it carries not only the payout eye device, but also all the other components and even other axes that are required to move the payout eye device. So this is the carriage axis. On this carriage axis is mounted the payout eye device. The payout eye device winds wetted filament over the mandrel. It sits on a platform like that. And then the payout eye has a roll axis or tilt axis. This axis allows the payout eye device, which is a horizontally positioned roller at its tip, allows it to tilt like this, okay, or roll. So this is the payout eye roll axis, right? Payout eye roll axis. So since we're classifying components based on the axis, we'll call this the payout eye roll axis components, just like we did before for the other one. So the payout eye device has the ability to roll, and it has a range of motion of 90 degrees only. So this is a 90-degree range of motion. And of course, we need to talk about the angles and distances because we're talking about the kinematic design, which is basically discussing how the machine will move, okay? The range of motion for the various axes. So for the mandrel rotation axis, this rotates 360 degrees many times, ongoing. So we'll program it to rotate as many times as are needed for the payout eye device to fully wind the entire surface of the mandrel, which we'll call one layer. So when you finish winding the filament over the entire surface of the mandrel without any gaps, you have one layer, okay? And there are many different types of layers. So there are going to be the helical layers, there are going to be the hoop layers, and so on and so forth. So, but we'll talk about that in detail when we begin to discuss the actual programming and the winding pattern. There are many winding patterns depending on the application, but we'll talk about them and the factors that govern those winding patterns. So this is the payout eye roll axis. Then we are considering adding another axis here, which is the payout eye yaw axis. So if you're familiar with aerodynamics, you may be familiar with the term yaw, I'm sure, or you may have come across it in some other discipline. So basically, while the payout eye axis roll involves the payout eye device moving like this, 90 degrees, okay? The payout eye yaw axis moves it in this way. So it rotates it with a vertical, around a vertical axis, okay? So the payout eye yaw axis is equivalent to moving like this. The payout eye roll axis is equivalent to moving like this. So I'm sure that's clear. So we're talking about the components or the classifications of classification of the components of the machine. So this will be the payout eye yaw. And by the way, yaw is spelled Y-A-W, in case you can't see clearly what I've written. Payout eye yaw axis components. Basically, components required to move the payout eye device in the way that we've just described. And it also has a 90-degree range of motion. So you can move 45 degrees like this and 45 degrees like this, making it 90. Same as the roll axis. For the carriage axis is the platform upon which the entire assembly of all of these, the payout eye roll axis, payout eye yaw axis, all those components all sit on the carriage. So this carriage assembly has a range of motion of 2 meters along the length of this carriage. It's like imagine a train, okay, running along a track, moving back and forth. That's what this is. The carriage axis rolls, rides along this rail, left and right, and its full range of motion is 2 meters. That's the allowance we made for it to be able to fully access the ends of the cylinder properly. And why do we even have these additional axes? We have these axes because of the complexity of of the pressure vessel, particularly around the bottom and the top caps, which are shaped as domes. Okay. For the cylindrical segment of the machine of the mandrel, a simple motion along the carriage axis would be sufficient for the payout eye axis to simply wind a filament. If you're doing simple hoop winds, or when you're doing helical winds at a particular angle, you will run into difficulties if you only have that degree of freedom riding on this axis and then the mandrel rotating. You need the payout eye device to be able to position and face the mandrel more directly. You want the payout eye device to dispense filaments at 90 degrees. You want the filaments to be coming out at 90 degrees. You don't want it coming out at awkward angles, which will cause it to have inconsistent patterns. It will not lie in the same way. You may have variation of the width and so on and so forth. So these are the reasons why we have multiple axes. It's also very important because when you're winding the material, when you're feeding the material, it allows you to more carefully and more consistently position the filament, because sometimes when you're winding around the ends of around the domes, complicated shapes like that, if you don't have a program that accommodates the shape properly, you can have fibers slipping away from the initial position later. So for example, you can have this move over there, and then the fibers can lay down in the correct position. But as the machine moves back to continue the cycle, that fiber can leave that position. And when you have a gap there, a gap is a weakness in the component. So when you perform one complete layer, the expectation is that every inch, every millimeter, square millimeter of the surface of that mandrel has been covered with the filament. Any gaps are weaknesses. So if the cylinder were to be inflated or put under pressure, that would be a likely failure point. We will now go ahead and discuss the carriage axis components in greater detail. So as initially sketched before, there's a platform that the carriage axis sits on. The carriage axis supports the payout eye device. The payout eye device has a tube through which the fibers are fed. So this is let these lines represent the filament being fed into the payout eye um, roller. These filaments are going to be on bobbins that are mounted on a frame. So they're fed from bobbins mounted on a frame. They're passed through a tensioner. They go through rollers and are immersed in activated epoxy resin or polyester resin, depending on what the winding is being done with. And then they move into the payout eye device, going through this opening to a roller, which is called the payout eye. This is what the payout eye roller looks like. And I'll discuss the roller more specifically. It has a special profile that allows it to perform the task it's designed to perform. Okay, that's what it looks like. The fibers wind over the roller and they are fed to the mandrel. They wind around the mandrel. So let's draw a small cylinder here to represent the mandrel. And let's draw lines on the mandrel to represent fibers being wound over the mandrel, so on. So this is a simplified look of what the carriage axis looks like. So the carriage axis supports all of these. This cylinder within here is mounted on bearings on both ends, and there is a half gear, okay? Because it has a degree of motion of 90 degrees, although the half gear is allows you to have 180 degrees motion. So we have, an allowance to be able to change our minds during the programming part. But at a minimum, we have at least 90 degrees here. But in actual fact, we have up to 180 degrees. So this cylinder you see here has the ability to roll. So this is the mandrel payout. This is the payout eye roll axis. It gives it that degree of freedom to move 90 degrees. And as I said, that's done with a a half spur gear, half of a spur gear. Now, what I mean by half of a spur gear is, you know what a gear is, right? It's got teeth all around it. But in this case, our application, we're not going to rotate the device 360 degrees, which is a complete rotation. It's going occasionally going to move 45 degrees in one direction, 45 degrees in the other direction. So actually, we don't need the other half of the gear. Okay, we don't need this other half of the gear. This is the center. So we just need a part of that gear to minimize material use. The rest of the gear will never actually will never actually be used. So there's no point using the full gear. Okay, then the payout eye device, as I described, it's got a cylinder through which the wetted fibers are fed over rollers onto the mandrel. Okay, but in order to implement the yaw axis that we just described, YAW axis, yaw, payout eye yaw axis, which allows the payout eye device to move in this way as we described. Okay, the roll axis moves the roller in that way, and the yaw axis moves it in this way. In order to implement that, this whole platform needs to sit on a pivot, and similarly, it will be driven by a half spur gear. Okay, so let us imagine these are the teeth, not a complete spur gear. We have a small pinion here, and we're going to calculate the transmission ratios, the loads and torques. But because we're talking about kinematics right now, we're not talking about force analysis or load analysis. We're talking about range of motion, angles, distances. That's what fits within the scope of kinematics or the kinematic design. So the whole payout eye device sits on a pivot. The pivot is driven by half of a spur gear or a fraction of a spur gear. It can be 25% of a spur gear, 40%. So when the actual design, when we get to the actual design, I will calculate the exact number. I'm not going to make a large gear for no point. And the fabrication technique we're using to make the gear is it really doesn't have to be a full gear for us to make it accurately. And we'll talk about that when we get there. We'll discuss in detail. So this is a fraction of a spur gear. Could be half, could be less than that. But in essence, all we need to do is move this 90 degrees, 45 degrees to the left, 45 degrees to the right. And then all of this whole assembly now, okay, the entire assembly rides on two rails, which are called the guide rails, and they run through the length, as I described before in the first sketch, through the length of the machine. So this whole assembly now moves all the way to the end, to both ends, which is a total of 2 meters. The total range of motion is 2 meters, okay, for the carriage axis. So this brief discussion has discussed the carriage axis. We'll do detailed design of all the components for the payout eye roll axis, as well as the payout eye yaw axis. In order to effect motion to each of these axes, you need a transmission, and there's going to be a design for each of those transmissions, and estimating the loads, estimating the power requirement for the motors, and calculating the transmission ratios and all of those things. So that brings us to the end of this aspect of the kinematic design. The only other thing I've not discussed, and I'm going to discuss briefly, is the mandrel rotation axis. So similar to the first sketch, we have the frame standing on the ground. We've got the mandrel rotation axis. We've got the mandrel. Then we need a mechanism for attaching the mandrel, mounting the mandrel to the machine. So you have to be able to lift the mandrel, place it on the machine, tighten it properly, and before running it. So those are components that will be discussed. So here, all that the mandrel rotation axis does is hold the mandrel in position and rotate it along its central axis. Okay, in a controlled way, according to a computer program. We'll write a program to do all of this. So what's involved here really is a transmission and a motor mounted on either of these ends. My preference is this end. So that transmission will drive this, and all of that motion will be coordinated. All of these, it will all be happening at the same time because the program will simultaneously control all axes, whether it's 3 axes or 4 axes. If we have enough time, we'll make it 4. So that's that brings us to the end of the kinematic design. So the conclusion is we know the range of motion now for all of the axes, which is the starting point for mechanical design. Okay, so the starting point for load analysis and other aspects of our design. So now we can individually handle we can go to the load analysis aspect and begin to discuss what all of those decisions imply.